Thank you, Martin, for the introduction, and thank you, the organizing committee, for the opportunity to talk today about the LISA interferometric detection system. Probably many talks ago on Monday, you remember that Filippo showed the IDS. It was a green box somewhere in the bottom of a screen that was shown as one of the ESA member state contributions to the LISA payload system. So I want to dive into this box and bring you closer to what it means and all of the team that is behind the hardware that we're developing, and I'm talking on the behalf of the IDS team. So before I jump into IDS, I would like to start with the baseline of the optical metrology system. So LISA will measure distance between two test masses or pair of test masses using interferometry technique, and the passing gravitational wave will cause the displacement of the order of tens of picometers, let's say, and to round up, and this sets the baseline of our measurement, so it says the sensitivity that we are targeting. So these displacements would we measure using the heterodyne interferometry, and here is a cartoon representation. We have the incoming laser light Rx that comes from the far spacecraft that is compared to local oscillator. In LISA, this beam is called Tx. And what our photodetectors see is the heterodyne signal that is of the frequency of the difference of the frequencies of those two beams. Now, when we have the passing gravitational wave, it creates the phase shift in this incoming beam. And this phase shift will be preserved and even pronounced on the lower frequency heterodyne signal, as you can see here. And this phase shift is what we want to measure. Now, each of the spacecraft can act as a transponder, so it locks its laser to the incoming laser and sends it back. And we can resolve the full constellation interferometry in post-processing by using TDI technique. This is something that Olaf told us about on Tuesday, I believe. So let's jump into what the primary objective of the interferometric detection system is. As I said, we want to measure the phase of the light, and the objective of IDS is to provide the means for the three interferometers. So here on this cartoonish version of LISA, we have the spacecraft, one of the spacecraft sending light to the far spacecraft, and we have the science interferometer where we superpose the local laser beam Tx with this received Rx. We have the test mass interferometer where we have the local laser Tx that is compared to the reference beam that comes from the adjacent bench on the same spacecraft. It's not shown here. And we have the reference interferometer that also compares this Tx laser with the reference laser from adjacent bench. This time just the local laser does not bounce, retroflects from the test mass. So our primary requirement is to measure those three interferometers with the precision of 9 picometers per root hertz in a science interferometer, 2.6 picometers per root hertz in a test mass interferometer, and 2 picometers for the reference interferometer. Other requirement that IDS has to fulfill is provide the measurement of the differential wavefront sensing with the noise floor of better than 13 nanoradians per root hertz in science interferometer and better than 5 nanoradians per root hertz in test mass interferometers measured in the reference frame of the optical bench. And those requirements sets the whole baseline in the functions that IDS has to fulfill. So what are those functions? First, as I already mentioned, we have to measure the bit node signal. Something that Olaf mentioned in his talk, we have to precisely know about timestamp of our measurement. So IDS has to provide the precise knowledge, precise and accurate knowledge of the time of the measurement. To further reduce the noise in post-processing, we also have to know the absolute distance between the far spacecraft, so we have to provide the ranging. We also have to provide the balance detection to reduce stray light noise, compensation of noises like tilt-link coupling, compensate for point-ahead angle. Additional function is to provide the data link between a far spacecraft to send the science data and maintenance data, as well as the commands between the spacecraft. We also have to provide the means for the beat node acquisition, initial constellation acquisition, and as everything, all the units that fly in space, we have to provide the relevant redundancy to ensure the successful mission. So to fulfill all of those functions, IDS consists of the following units. We have optical bench. Yuan was talking about this yesterday. So optical bench assembly hosts following units: quadrant photoreceivers, beam alignment mechanism, point-ahead angle mechanism, and fiber switch unit actuator. Optical bench interfaces optically with the laser system on one side to receive the TX light from laser. Also interfaces with the telescope to exchange light between the far spacecraft, and the GRS head to provide the test mass interferometer. IDS also consists of the phase meter system, which is interferometric processing unit and phase meter control unit. Phase meter control unit interfaces with MOSA, with LISA spacecraft. We also have optical bench mechanism control unit that controls our hosted units on the optical bench. And we also are responsible to provide all of the harness, so the things that connect all of the bits together and make it work as one system. And this is basically the outline of my talk. I'm going to be speaking about each of those systems. So starting with the optical bench assembly, we heard a lot yesterday about this in Yuan's talk, which makes my job much easier today. So I will just summarize briefly the key functions for the IDS. So optical bench is being developed and provided to LISA by UK team, UK ATC, and University of Glasgow. Its main functions is to host the 3 interferometers that I mentioned. It provides by providing the interface with the LISA laser and connect via optical fibers. It hosts the quadrant photoreceivers, which is the first part of the readout system. It provides the tilt-link coupling compensation by, on one hand, the optical systems like imaging system in front of QPRs, as well as beam alignment mechanism compensation. It provides the point-ahead angle via hosting the point-ahead angle mechanism. We can see those here. And provides a necessary redundancy for the interface of the laser system and the optical bench, as well as 2 optical benches being connected via backlink by hosting the fiber switch unit that switches between nominal and redundant fibers. So the key performance requirements of the optical bench, as we've heard yesterday, is to provide high dimensional stability of the optics. Therefore, the optical bench is manufactured in a low thermal expansion ceramic coefficient ceramic, 0 Dur. We also heard the whole process that Yuan walked us through, how accurately place the optics and bond the optics on the surface of the base plate. This is also a requirement for hosted units, how precisely they have to be placed on the optical bench. Optical bench also enables provides the means for the balance detection to minimize stray light by hosting pairs of the QPRs in each of the interferometer, which allows us to later subtract this noise in post-processing. It also, as I already mentioned, provides the compensation of tilt-link coupling. So now I would like to talk about the interferometric readout system, and first part that is hosted on the optical bench are the quadrant photoreceivers. Quadrant photoreceivers are being developed in Netherlands by Esron and Nikev with the support of KU Leuven that is responsible for the front-end electronics. So quadrant photoreceivers transform the optical signal coming from the 3 interferometers into photocurrent. This photocurrent is being amplified in transimpedance amplifiers and sent to the interferometric processing unit for further processing. We use quadrant photoreceivers to be able to measure the DWS signals. So just a quick reminder, if we have the wavefront, one of the wavefronts that is falling on such a quad photodetectors tilted, we'll see either advancement or delay of the phase read in a particular segment, and that reflects the tilt, so pitch or yaw of the incoming wavefront, and indicating the tilt on the far spacecraft, for example, or the test mass. And this signal is being used by the DFAX system to correct for the spacecraft attitude. It also is used in the post-processing to correct for the tilt-length coupling noise. And the key requirements of those quadrant photoreceivers is to provide the low noise performance and high responsivity. Here is the rendering of how those quadrant photodeceivers look like in its mounting brackets. If you're interested in more details, Timesh was giving his talk on Tuesday, I believe, so you can probably find him or go back to his presentation materials. And as I mentioned, the quadrant photoreceivers, we read the optical signal from the 3 interferometers and transform it into photocurrent, and then they send it to the interferometric processing unit, or IPU. IPU is being developed by the Max Planck Institute in Hanover, Germany, with the support of DLR, so German space agency. So IPU extracts the phase information, so actually scientific readout from this photocurrent, and sends it further to the phase meter control unit. It also provides the timestamping and for the measurement, as well as ensures the distribution of its own clock into the far spacecraft and the second interferometric processing unit on the same on the second MOSA on the same spacecraft via sending the clock sideband modulation signal into the laser system. So it provides the laser system with the so-called clock sideband. This is something Tony mentioned in his talk yesterday. IPU also provides the PRN ranging and extracts the information of the PRN code coming from the science interferometer. That's for the TDI noise reduction. If you're interested a little bit more about PRN codes and PRN ranging, this is a talk on Friday by Pascal in the Constellation session. IPU also provides the support for the initial bit node acquisition by sending the information about the bit node frequency into the PCU. And then PCU. So PCU receives the scientific data from the IPU. PCU is being developed, it will be delivered to Lisa and Ideas from Denmark with the scientific support of Max Planck Institute, AI Hanover. It receives the scientific data from the IPU and prepares it for the further downlink to Earth by downsampling it to the required frequency rate and sends it further to the onboard computer. PCU also receives the bit node frequency from the IPU to provide the laser system with the frequency control, and it's not only for the laser locking, but also to ensure that the whole constellation follows the frequency plan. It also provides, the PCU provides the IPU with the control signal and the clock main clock information from the spacecraft. PCU provides the laser system with the ranging modulation as well as the modulation of the data that needs to be sent or the commands that need to be sent to the FAR spacecraft from the onboard computer. I know I just hear myself an echo if I stood in the wrong spot or it's being a little bit disturbing. So just a quick summary of the readout system. So we have the QPRs that read the heterodyne optical signal, amplify it and send it to IPU to be further extracted, so extracted the scientific information, and sent to PCU to be downsampled into the required data rate. That's being provided to the onboard computer for further downlink to Earth or sent to the FAR spacecraft to be downlinked to Earth. Now, let's go back to the hosted units. They're on the optical bench. I already talked about the QPR, so let's right now go and talk about BAM, PAM, and FSUA. So the next one is BAM. Beam alignment mechanism provide the compensation of the tilthulan coupling noise. Tilthulan coupling noise comes from the fact that when we have the jitter of the FAR spacecraft, and in addition, any internal misalignments on the optic, as well as respective misalignment between the optical bench and the test mass, or optical bench and the telescope. There were already 2 talks on tilthulan coupling on Tuesday by Marie and Zara. I know that there is a lot of posters today in the afternoons. I'm not listing all of them because that will take the full slide, but please, if you're interested in this topic, go and check with them. So to compensate for this TTL noise, IDS is providing the beam alignment mechanism that is being developed by KU Leuven in Belgium with its industrial partner Redwire. The BAM mechanism is composed of 2 optical components, tilted optical plates that can rotate around its central axis, providing the lateral displacement that can be provide the compensations of this TTO. And the maximum displacement they can provide is up to 230 micrometers. This will be done once we know what are the coefficients of the TTL for that particular spacecraft. Here is the rendering of a BAM courtesy of Redwire. That's how it's going to look sitting on the optical bench. Now, IDS needs to provide the point-ahead angle mechanism. Unfortunately, because it's PDF, my video is not working, but I think everyone is familiar with those renderings where we have the LISA constellation running around the sun. So what is missing in those ones is the fact that we actually have a delay between spacecraft. The light travels approximately 8 seconds between those. So if we are on a spacecraft 1 and we want to send our light to spacecraft 2, we have to point where the spacecraft will be in approximately 8 seconds, not where it is right now. And that creates the static offset between those 2 that we have to compensate for. We also have to compensate for any off-the-plane point-ahead angle changes due to the spacecraft move, and that can be done only on the optical bench. Therefore, the Netherlands company TNO is developing the point-ahead angle mechanism, which is the single optical component that rotates around the axis that is coincidence with the surface of that optic to minimize the noise and the piston effect coming from the rotation of that optic. And here is the picture of the actual unit, courtesy of a TNO. So that's how it looks. Now, the last of the hosted units is the fiber switch unit actuator. As I mentioned, we have to provide the necessary redundancy, and one of them is to be able to switch between redundant and nominal fibers that are interfacing from the laser system to the optical bench and to optical benches interfacing each other via backlink fiber. And for that, the Czechia Institute of Science is providing the FSUA that is shown here, and inside it has two wave plates, half wave plates, that together with the polarization component in front of the fibers in a rotation can switch between the polarization, select the polarization, select which fiber will receive the light. So in itself, it also has, you can see, redundancy by having two independently rotating wave plates. And now, all of those three mechanisms has to be controlled, and for that, we have the optical bench mechanical control unit, or OBMCU, being developed by Esron in Netherlands together with Czechia Academy on Science. So here is the OBMCU. It sets the position of the hosted unit to the desired position. It by itself is being commanded by the onboard computer. It consists of the following unit. It has digital control unit and power supply, as well as the front-end electronics for each of the hosted units. The PAM-FE is being developed by the same team from Esron, while the FSUA and BAM-FEs are being developed respectively by Czechia and Belgium, the same teams that are developing the mechanism themselves. Last but not least, a big part of the IDS system is to provide the verification of its all units. And that, of course, comes down to verifying each of the units and interfaces themselves, but however, not everything can be verified in that way. Therefore, we are developing the so-called end-to-end test where we encapsulate the full IDS system. And this campaign is led by the LISA France, with CNES being the leader of the effort to provide the functional and performance test of the full IDS system. So let me quickly walk you through this schematic. We have the units under test, which is optical bench assembly, IPU, PCU, and OBMCU. Those are the IDS units. The optical bench assembly interfaces with the beam simulator. Beam simulators act as a far spacecraft as well as the adjacent bench on the same spacecraft. There was more about this in Maxim's talk on Wednesday, I believe, so please check out the notes from his talk if you're interested. And we also have the test mass simulator on the other side that acts as a test mass. All of those units are enclosed in a stable structure to provide relevant stability for the test, and this all is enclosed in the optical vacuum chamber for the relevant environmental stability. We also have the optical ground support equipment, laser GSC, that acts as a TX laser for the adjacent bench and fire spacecraft, providing RX beam to optical bench assembly and the reference beam for the backlink. We have the stray light OGC for the measurement of a stray light on the optical bench. We have the electrical GSC that acts as a full spacecraft and run the whole measurement by commanding units and collecting all the data. We have the phase meter ground support equipment that acts as a phase meter again on the same bench on the far spacecraft, depends on the need and current test. This is the unique one of the unique units in this setup because it's being developed by University of Hamburg, being delivered especially for the test. We also have a laser. This will be provided by our colleagues from NASA, ETU laser for the so-called IDS Plus test. What is not shown in this picture is all of the facilities that are behind this test, all of the clean rooms, control rooms, and everything that our colleagues in CNES are developing to provide this test. And here is just a rendering and quick schematic on how it looks. We have the stable structure together with beam simulator, optical bench, and test mass simulator, the IDS units under test, IPU, PCU, and OB MCU sitting in the electronic vacuum chamber together with NASA's ETU laser, the stable structure in the optical vacuum chamber. And this is how the whole test setup will look like. And this is my last slide, and I want to thank you for your attention. And there's lots of name behind those logos. That's why I just stick to the logos on the last slide. Thank you. I'm happy to take your questions.
Thank you very much, Ada. So we have time for a few questions. Do we have any? We've got one here. Where are our microphones? Microphones on the way.
Thank you for a great talk. The question is about the end-to-end test bed, and I'm over here. Right behind. Hello, it's hard to see. The end-to-end test bed, and in terms of the beam expander, I saw that you're doing both functional and performance testing. Are you attempting to do picometers of measurement between the expanded beam or the beams between the test bed and the optical bench?
Well, so we will obviously measure the noise coming from the beam simulator as well. So we can only measure as good as we have those two. But yes, the answer is we are attempting to measure the performance of the full system. Yeah.
We've got a question over this side. From Natalia. Just want to take mine, Natalia.
Thank you for an interesting talk. Just a question on your last slide when you were showing that before that, why do you use a different phase mirror than from the flight phase mirror for testing, or did I misunderstood something?
No, this is a good question. So we're using the ground support equipment phase meter for the test. It has to provide all of the functionality performance as the phase meter that we're building for LISA. This is true. However, it doesn't have to be made out of all of the same flight components and all of the same procedures. It can be, a little bit cheaper and simpler or bigger. It doesn't have to, be the same form factor.
Okay. Any final questions? Doesn't look like it. Well, we are a bit over time, so let's thank Ada and all the speakers again.